Um, hey everyone, thanks a lot for joining. So today we are, I think we started Go MLOps days last Thursday. So we start with model training with Argo workflows, how we build a system in Glovo using Argo workflows, leveraging power of Kubernetes. Then we did have discussions around best practices. And yesterday we heard from Alexei how he is productionizing models in Anlaytics. So now I think we are going into the next phase where you have your model in production, how you can monitor these models efficiently. So today we have Emeli and Elena from Evidently. So Evidently is an open source tool, which I think they will introduce you and share more information about it. So they are also very active participants in MLOps community, and we'll be seeing their faces time to time in different events in MLOps. So happy, and it's a great pleasure to have you both here. So I hope everyone in this session enjoys this one, and if you are watching it afterwards, I hope it will be useful for you as well. So over to you guys.
Hi, thank you so much. We are very happy to be here, and I believe we can start like now.
Yeah, sure.
Perfect. So I'm trying to share my screen, and hopefully you should see it right now.
Yeah, we do.
Perfect. So my name is Emeli, and I'm happy to be here today. I'm going to share with you some thoughts on how we can set up the monitoring for machine learning models. And today we are going to discuss what can happen with machine learning models since we put them in production. And later I'm going to share with you a demo using Jupyter Notebook with Evidently, an open source tool to validate and monitor machine learning models. So now I'm CTO and co-founder at Evidently.ai. This is the tool which I'm going to introduce to you. With help of this tool, you can build very nice interactive dashboards and export them to share with the team. And prior to Evidently, I worked at the Yandex Data Factory when we helped to build many different solutions on top of data. So it was different database services. So today I'm going to use this experience to discuss what can happen with machine learning models and how we can account to it. And first of all, let's discuss how machine learning models failed in production, because, well, everybody knows that build a successful machine learning model is a tough task itself, because we need to put together many data from different data sources. Then we need to perform a solid feature engineering process on top of it, build machine learning model, validate it, then build the service. And that's the moment when we just start working with the model in production, right? And since we start working in production, the model already starts to generate some value, and each failure costs something. So it makes sense to make sure that we know what is happening, and we can make sure that models work as we expected. So what can happen? In many cases, when something is wrong with the models, that's because the input data is wrong. It can happen for many different reasons related to data quality and integrity. For example, there can be some data processing issues like broken pipelines or unexpected infrastructure updates, especially when we use third-party data, right? So sometimes we can use the wrong data sources, and this affects model a lot, because that affects the model input data. Sometimes we can use some systems like CRM, which has a lot of different users, and sometimes users make some changes like update the CRM data schema, for example, rename a couple of columns or move it around, and of course it influences the model. Or data can be lost at the source. For example, data can be lost physically when you have some broken physical sensors, or the logging can be implemented incorrectly. So many things can happen. This is something that you can catch with help of data quality and data integrity monitoring, especially if you have a big data engineering team. But sometimes you can use more complicated service structures. For example, when you have many different machine learning models which interact together. For example, like here, when we have very nice service to recommend the best possible route to get from point A to point B, for making such recommendations, we need to build many different models, at least one to predict the traffic jams on top of the aggregated traffic data. Then the second route to predict the estimated time to arrival, right? And on top of these models, we can create the recommendations. And obviously, if something is wrong with the first model, which predicts the traffic jams, then all the other models will suffer. So this is something that we need definitely monitor and make sure works well. If the data engineering team keeps their job done, anyway, we can suffer from things which called data drift. There can be concept drift when something is wrong with our target function, the value we're trying to predict, or it can be a data drift, which is related to the input data features. Gradual concept drift, this is the case where the world around us is changing and our target events start changes together with it. For example, this drift can be gradual when we have a lot of small changes which accumulate over time, and because of this, the model's quality, for example, accuracy, starts to degrade. Or this drift can be sudden. The recent pandemic is a perfect example of this situation. Like almost overnight, a lot of model starts worked incorrectly because a lot of patterns has changed. A lot of flights were declined. So many things has changed almost overnight. So we should be able to account for such cases. And this is why we need to set up monitoring to make sure that there is no such changes in our target function. So pretty same thing can happen with the input features. The distributions of input features can change, and this can happen because of many different reasons. Just because we have natural trends in our environment, or because some events happened. For example, we could launch a very nice marketing campaign, and we can see certain distribution changes in our user acquisition channel. For example, before we had most of our new users come from paid search, but after very nice successful marketing campaign, you could get a lot of new users from social media services. And if our machine learning model, which, for example, predicts churn or recommends something, was trained on top of the users, mostly from paid search, right? Because previously we had a lot of users from this channel, then it can work just a bit worse for users from social media if they have specific patterns in behavior, and we just didn't demonstrate a lot of such users to our machine learning model during the training period. And this is the reason why it makes sense to monitor and account for data drift and make sure that our model is prepared to work with some new data and some changed distributions. So now we know that there are many different things that can happen with the model when it's already in production and generate some value. How to prepare to it? The answer is monitoring. So one can say we have production services for many years, for decades. So why cannot we just reuse the existing monitoring schemas for our machine learning based services? Because, well, it's a software, right? So we can definitely do it. So I'm fully agree there because it's service, first of all, and we definitely need to set up the service health monitoring, which include things like uptime monitoring, memory usage, CPU usage, latency, and things like this, right? So this the thing that we must implement when we have production service. But together with this layer, we have a lot of things related to data, right? So we need to monitor models quality, data drift, concept drift, and things like this. This all related to model health and data health. And this is why we should care about monitoring of data-based services in general and implement the extra layer of such monitoring. Before we discuss how to monitor, let's discuss the tools and infrastructure. Here, I believe that the database service will not be the first service we are going to monitor, because if it is, then it makes sense to first maybe discuss the infrastructure in more details. But if it's not the first one, then I will just add that you can reuse the existing infrastructure to monitor database service. So if, for example, you use the primitives or other database to collect the events, the logs, and, for example, use Grafana or Zabbix to visualize the dashboards and set up an alert, then you can perfectly reuse the same tools to monitor your database services. Maybe you need to add some more events to calculate more metrics, to calculate some specific metrics, but from the infrastructure point of view, these standard tools are very nice choice for database services. If, for example, you have batch models, then you can probably reuse the API tools that you already have. It can be tools like Looker or Tableau, or maybe you even implemented some custom solution using Python and libraries like Matplotlib, Seaborn, Plotly. This is the very nice starting point, because if you have batch models, then probably you have some gap between you generate some predictions or recommendations or other models output, right? And the moment that you need to start using this output. So during this gap, you probably can create some visualizations, generate some dashboards, calculate a couple of metrics, and make sure that the output you're about to use is within the expected ranges, and you agree with this output. So this is what I wanted to mention about tools. And how to start? I believe it's super important to be pragmatic there, because, well, building a solid, complex monitoring approach is a tough task by itself, right? In big IT companies, in many cases, we have the special team dedicated to building, updating, and support monitoring system. So depending on the resources you have, you can decide on simpler or more complex structure of your monitoring system. So I believe it's very important to take into account the use case importance, because the different tasks can be more or less important. There can have different economic value, right? The errors can cost different, and risks as well. So this is something that we need to care about. Second is the complexity of the service, because the more data sources you have, the more complex pipelines you have, the more things can go wrong. Well, so batch and real time are different things, and depending on this, we need to decide whether we should to have more complex or more simple monitoring system. And of course, team resources are super important, because if you have limited amount of resource even to build the machine learning models, then probably you should use more simple monitoring system, because you need to save some resources to build your first service as well. So I'm going to move to the demo, because I believe everybody already want to see how to build something using Python. So I'm going to do it right now. Just to mention that for the demo, we are going to use publicly available dataset, which is bike demand prediction. This is the dataset which is used to predict how many bikes will be taken into a rental based on the weather conditions, based on the season and the time. So let's move to the demo and see how we can create the interactive dashboards and figure out what is happening with our model. So for doing this, I'm going to start new screen share. And hopefully you will see my code like now. Yeah, perfect. So let's do it. I'm going to use Evidently tool to build the interactive dashboard. I believe it's worth mention again that it's open source, so you can analyze the code if you're interested, or just install Evidently package using pip command and build the same dashboards for your machine learning models. So let's start from importing a couple of things. I'm going to use standard libraries like pandas to work with table data, NumPy, datetime, and scikit-learn to build the model. Together with this, I'm going to import dashboard from Evidently dashboard to build the dashboard, obviously, and import list of tabs, because we can build pretty complicated dashboard using different tabs, which tab related to the specific kind of analysis. So there we are interested into data drift analysis, into target drift analysis, and into regression performance, because we are going to build the regression model to predict the amount of bikes taken into a rental. So if you want to play around with some new libraries and maybe you're not ready to install it for the whole system, then maybe it makes sense for you to create specific virtual environment and install a library there. So then play around and decide whether you're going to continue using it and maybe then install it for the whole system or continue working with virtual environment. So that's pretty much what we wanted to import there. And let's read the data. So I already loaded this data to my system, so I can just use the pandas read CSV command. And let's see how the raw data looks like. You can see that this is the plain table. I use my datetime as an index because later on I'm going to select the train and test data based on the datetime, and it's very convenient when you can perform log, when you can use log command, right, and apply it to the index. So that's exactly why I decided to do it. And let's skip the part where we perform a lot of experiments. I'm fully agree that we definitely, if it was the real project, we would do a lot of experiments. We will use the cross-validation to calculate models performance and actually start from exploratory data analysis, right, to see what is happening in our data set. But we know that this is the standard data set and we know that it's more or less okay. So let's perform the simple feature engineering, because we know that the demand on the bikes is affected by the seasons. So it makes sense to calculate months, hour, and weekday features. So let's do it. Likely we have pandas data frame, so it's easy to add the additional column using these commands, and just with help of the map function, take the month, hour, and weekday from the raw data. So that's how we created the additional features. Now let's see how it looks like. And yes, we just added a couple of columns to our data set. Then let's move to the model training part. And for doing this, let's prepare a couple of variables which we are going to reuse later. So our target function is called count. It's available there. So let's create the variable target and memorize the name of the target function. So our prediction are going to be prediction, pretty standard name. And we have two types of features, numerical and categorical. So let's create the lists of the categorical features names, which is season, holiday, and working day. And all the other features are numerical. So let's create such list. It's there. Okay, then let's skip split our data into two parts. First will be reference part, which we are going to use for model training, and the production part. On top of production data, we will simulate the production usage of our model and perform the model quality analysis. So let's split our data using log command. Luckily, we have datetime as an index, so we can just put our data like there right here and perform the split. So our reference and production, of course, will have the same structure. And now we have everything in our hands to build the model. And you know, if we do not want to perform a lot of the experiments, you can just choose an algorithm which is not tend to overfitting a lot, and the algorithms which are based on the bagging technique are best choice there. So let's choose the random forest regressor on top of decision trees, which is the bagging algorithm, and we can kind of skip hyperparameter selection procedure because, well, we will have a lot of decision trees, and we are kind of sure that our model will not be overfitted too much. So let's do that. And let's train our model on top of the reference dataset. So for doing this, we will select features for our model training, which is numerical features and categorical features. It makes sense because we have some additional columns in our dataset. So this is why we perform the selection of the columns. And our target function is called count, which we save in the target variable. So we can just run this command and feed the model, which is super fast because I have only 50 trees, and that's it. So after fitting the model, we can generate our predictions, and we need to generate it for both our reference dataset and production dataset. So let's do it using command predict. And let's add this data into our data frames for reference and production data. So here it is. Now we have everything set up to perform the model's quality analysis. And before we move into monitoring, let's make sure that our model works. Right? For doing this, we can analyze the model's performance on top of the reference data set, because, well, if it doesn't work on top of the training data, then it makes no sense to continue analyze the model's performance. But if it works on top of the training data, then it makes sense to analyze the quality on the holdout data set, and then if everything okay, use this model for other data. Other available data, let's call it like this. So for analyze machine learning models performance, you can calculate quality metrics, or we can create a dashboard which already includes some metrics and some visualization. For doing this, I'm going to use Evidently tool, and before use it, we need to prepare some additional mapping, which I call column mapping. This is the standard Python dictionary, which contains the information about target name, prediction name, and type of features. To be honest, Evidently can parse the structure of the data automatically, so we can just skip this part and just create the dashboard without having the column mapping. But in this case, the parsing will happen automatically. So the tool will expect the target function is called target. For our data set, it's not true because our target function is called count. The tool will also expect that our prediction function is called prediction, which is true for us. And it will parse the type of the features based on the data columns type. So all numerical type of data will be interpreted as numerical features, and all the object type will be interpreted as the categorical. So for us, it's not the best solution because we have some categorical features encoded as numerical, and this is something that we usually do when we build the machine learning model on top of the categorical features. We can use different kind of feature encoding, starting from one-hot encoding or more complicated embeddings, for example. But anyway, it makes sense to tell to the tool explicitly when your data is categorical, especially when you encoded it with some digits. So let's now create the column mapping, which has pretty straightforward structure. So we just tell to the tool where we have our numerical categorical features and how we called our target and prediction. And now we have everything to build our first dashboard. Earlier, we imported dashboard object from Evidently dashboard. So we need to tell which kind of report we want to build. So there we can create the report containing many different tabs. And we are going to start from model's quality assessment. This is why we built the regression performance tab. And to calculate it, we need to run command calculate. And here we pass the reference data, the production data, and the column mapping. So now we started just from the reference data because we need to make sure that our model works, right? And this is why we just skip our test data set. And you can do the same when, for example, you do not have this test data set at all, right? In this case, we just pass known as the second data frame. And to build this dashboard inside of the Jupyter notebook, we can just run command show, like I just did, and you will have the visualization inside of your Jupyter notebook. So here we have the information about the type name. It's our regression model performance report, and our target column is called count, so we can check that Evidently parsed the data frame correctly. So we have some information about error. So our mean error is less than 1 byte, which is pretty good for training data, or maybe model is a bit overfitted. So let's see using some visualization. And we have mean absolute error, which is equal to 4 bytes, and mean absolute percentage error around 19%. Together with the quality metrics, we have a lot of dashboards. There, I mean, a lot of visual plots. And for example, we can see that our predicted values and our actual values are pretty close. So we have this diagonal line, which is the good signal it looks like we do not tend to underestimate or overestimate our demand, and model is pretty accurate. So here we have the plot with actual and predicted values in time, right? So we can, for example, zoom in into some specific regions and see what is happening. So, for example, around January 9, and you can see that our actual and predicted values are pretty close together. So we can, for example, move our panel, see other regions, and analyze the regions of our most interest. And of course, we can have the initial picture back. And if, for example, we need to export some visuals like this, because sometimes it makes sense to share such reports with someone, we can easily download it from there using this function, download plot as PNG, and have the PNG. Right, together with this, we have some plots of the year. For example, we have the absolute year predicted minus actual, and we have the absolute percentage year. So we can see that our year is around 0, right? So it's exactly what we want to have on top of our training data set. We have some information about year distribution. We can see that the mean year is equal to 0, and it's symmetric, so the distribution looks normally. And we have the normality test, so we can see that the actual dataset quantiles are pretty close to the theoretical quantiles, which is also a good signal. So yeah, there are pretty a lot of valuable information there. And together we have some information about our objects where we have the biggest errors. And we have this information with respect to the sign of the error. So the top 5% of objects where we tend to underestimate the target, and the top 5% when we tend to overestimate the target. In this case, we are not really interested in this analysis because we can see that we do not tend to have the higher in our data set. So we can just easily skip this part of the report because we are not interested. But we will analyze it later for our test data set. Together with the analysis of dashboard inside of Jupyter Notebook, which is very handy when you just building the model or running a bunch of experiments, sometimes it makes sense to create such dashboard as a separate HTML file and send it over to your colleague for performing some review, or maybe share it with the other members of your team who are not that happy with running Jupyter notebooks, but still interested in analyzing the model's quality and maybe giving some feedback on model behavior, right? For doing this, you can just use command save instead of command show after you calculated the dashboard, and just put there the path for your file. It will generate the HTML file, and this file will contain the same information. It will have the same structure, so it will be easy to send it over and share with the colleagues. So, okay, now we can see that our model works more or less good on top of our training data, and it makes sense to start analyzing the performance of our model on top of the holdout dataset. So let's simulate the process of production usage of our model. So we can split our test data set into weeks, and let's assume that we have our ground truth only weekly. So at the end of the first week of production usage of our model, we will be able to analyze the model's performance on top of the first week. At the end of the second week, we will be able to analyze the model performance for 2 weeks, and same, right? So let's analyze the model's quality weekly. And for doing this, we can reuse the same dashboard. So we can see that I'm not regenerating the regression performance dashboard object because it will have the same structure. I'm interested into regression performance dashboard, but I run calculate method again using different data frames. My reference will remain the same, but now instead of none, I will have the production data frame. So I will select only first week, starting from 29th of January and to the 7th of February, right? And the same column mapping. So I run calculate method again. This is the most complicated part in terms of machine time, right? And after I'm running the show command again, so here is my report. Now it's much bigger because it contains information for quality of our model, both on top of reference and first week of production, right? And we can compare the model errors. And obviously we can see that on top of our production data set, the error became bigger. This is something that we could expect because, well, it's the whole down data set. And let's see the visuals. I believe this is very handy because we can compare the same plots between reference and production, right? And you can see that, for example, for our production data set, we have the bigger error, right? Like our cloud became wider, it's not that diagonal comparing to the reference data set. So yes, our error is a bit bigger, but there are not a lot of outliers, right? So we cannot see any trend to underestimation or overestimation of the error because, well, at least visually it looks pretty similar. So we can continue the analyze plots. And for example, here we can see that our model is pretty nice into following of the trend, right? So sometimes we have some errors, especially at the highest values. So we can zoom in and analyze the worst places, right? So we can see that model is doing pretty good in terms of trend following, but in peaks moment, the error is pretty high. So let's continue the analysis. And we can see that, yes, sometimes we have higher errors. And I believe we will see same into the percentage here. Yeah, we can see these peaks here. And yes, you can see that our error distribution still have a peak value at 0, which is good, but the shape is changing, right? Okay. Let's continue our analysis and skip the rest of the report for now. And let's move to the second week. Here we can start from the same report calculation. So let's calculate the same dashboard using the second week of production, and let's see the visuals. Still, each of these reports you can save and share as a separate HTML file. So now our dashboard is ready, and you can see that, yes, our cloud is still pretty wide, right? And now we can see that we really tend to underestimate the demand, right? Because you can see that our actual value, which is the dark gray, is almost always a bit higher than our predicted value. And now we have all the reasons to start worrying about the underestimation, right? Let's zoom in and see. Yeah, we can see that almost always we tend to underestimate the demand. So we can continue the analysis, analyze the error predicted minus actual, and we can see that yes, our error is tend to be under the 0, right? So our predicted values almost always is pretty often, let's say, is less than actual. So we can move to the error distribution analysis, and we can see that the mean error is still equal to 0, which is good, but the deviation became wider and wider. We can start thinking that maybe there are some changes in our input features because, well, our model should somehow account to our target function, and maybe there are some drifts taking place there. So let's start from the target drift analysis, because first of all, it makes sense to analyze whether our target function has changed. For doing this, we can calculate the target drift dashboard. Here we have numerical target drift dashboard, and we can create another dashboard object, but now instead of regression performance tab, we can create the numerical target drift tab. We also imported it at the very beginning, so we can move and see. And again, the API is pretty same. So we created the dashboard, we calculated the information, and finally we run show method to create the dashboard inside of the Jupyter notebook. So we have a lot of visuals, and sometimes it takes time to plot it there inside of the Jupyter notebook, especially when you have Zoom that uses a lot of resources, right? But let's move back to the dashboard. So we can see that target drift is detected. We have a p-value is the pretty small. It's less than, yeah, so you can see it. And definitely you can see that the distribution of our target on top of the current data set, which is second week, and reference data set are different, right? You can see it here. And for example, we can see even ranges of our target function values. And we can see that during the training period, the reference data set, we had the maximum value of our demand equal to 290 bikes. But for our current data set, we have the much higher demand, right? 256 bikes. And yes, so the whole distribution is a bit different. Okay, let's see more information. And we have some additional visuals there. It's correlation between the target function and some numerical features. And we can see that they are actually different, especially in terms of wind speed, right? And what else? Humidity and temperature as well. So there are some differences. And there is another way of target values visualization. And we can see that we have much more values is higher demand during our second week of the model usage. So we should conclude that there is some changes in our target function. So let's now see if our model can catch that. And first way how we can analyze it is to measure if there is the prediction drift, because if our model is following the trend, right, then probably the predictions from the training period should differ from prediction of the second week period, right? Because, well, target function has changed. But we can see there that the prediction drift is not detected. It means that the distribution of our predictions stay the same. So model behaves more or less equally on top of the training data and second week of production data. And yes, we can see even visually that they look more similar, right? And we can see some prediction correlations there as well, but it's not that interesting because we already can see that there is no prediction drift. And there are some logic to it, right? First of all, we need to remind ourselves of the algorithm we used to model training, which was the random forest. And we know that the random forest is pretty stable in terms of the overfitting, right? And for example, comparing to some models which are much better into let's say linear trends following, for example, comparing to linear models, our random forest is tend to keep the same ranges for target function, which it set during the training period. So it's just because we use the trees and we average the values of the output values of trees, right? This is why the algorithm keeps the same ranges. So random forest is not tend to extrapolate too much, right? And this is what you can see in our visuals. So we can see there that our demand during the reference and current period of data is pretty equal. So it stays into equal ranges. Okay, probably we already know what is happening. So let's continue our analysis and move to our next week, so which is the 3 week. And I suggest us just generate the regression performance pretty quickly to see what is happening. So this should be pretty fast, I believe. Need to build some visuals. Yeah, it's there. So let's analyze how our error distribution looks like, because I'm most interested in this plot. So yes, you can see that we continue underestimate the demand, especially in peak periods, right? So let's move to our error. Yes, now it's pretty obvious that we underestimate the demand. So we can see that almost always our error is below the zero. So it's the very strong signal to start worrying about our model's quality, because comparing to the reference data, it differs a lot, right? So let's see the distribution of the error. And yes, now it even doesn't look normal, right? So we see that we have a strong trend to underestimation. So, okay, let's continue our analysis and let's see what we have there. We already know that we have some target drift, and probably if we calculate the target drift dashboard, for example, to compare reference data and our third week, we will see the same result. So there is the target drift there, but no prediction drift there. So let's make sure that it's happening. Yeah, so now we can clearly see that there is some target drift. So now there is even bigger difference in terms of ranges, right? But let's make sure that, yeah, there is still no prediction drift. So model doesn't catch in the trend. So now let's answer to the question, what is happening? So let's go back to our regression performance and finally analyze the last part of the report, because I promised that we are going to do this. So at the very last part of the regression performance report, we have some information about the specific regions of the year. So we have information about the year on top of the majority of our object, and we have separated groups, top 5% of objects where we tend to underestimate the target function, which is there, and top 5% of the objects when we tend to overestimate the target function, right? So it's out there. And we can see that the error is differ a lot, right? So let's see how it usually looks like. And yeah, we can see that we have some specific objects where we have much bigger error. And the question there is the following: whether there is some dependencies, some relationships between the error size and feature values. Because if it's out there, then maybe we can create some hypothesis of how we can fix the model by influencing on the features, right? So maybe there are some changes that can be influenced by some specific features, and then maybe we can fix it by rebuilding model without these features, or maybe just retraining model on top of the most recent part of the data, or maybe changing something in our feature engineering process. So let's figure out what is happening. And for doing this, we can use the error bias table, which have the information about the relation between the error size and feature values. So we have the information about feature name, feature type there, and we have the information about the mean feature values when it comes to numerical features for majority part of object, underestimation part of object, and our estimation part of object. I mean there that we have different objects where we tend to make bigger and lower error, and we can calculate the average value for each features only on top of these specific object regions, right? And on top of this analysis, we can calculate the range. So we can order our feature by the biggest difference between the means on top of different object groups and analyze them with priority. So we can see that the first feature is a temp, which feels like temperature. So let's open the first feature and see the plot. So we can see the distribution of feature values for majority objects, overestimation and underestimation, and we have such histogram for reference and current data. So majority is the less interested class, so let's just switch it off and compare the feature values for objects where we tend to underestimate and overestimate the demand. And we can see there that there is some dependency there. During the training period, on top of the reference data set, our error does not really depend on the temperature, right? So we, our model tended to underestimate and overestimate target function on top of all the regions of temperatures, like we can see there. So we can see that we underestimate and overestimate the demand pretty everywhere. But if we take a look at our right-hand side picture, we can see that for lower temperatures, we tend to overestimate the demand, right? But for higher temperatures, we tend to highly underestimate the demand, right? So maybe we have some dependency between the temperature and the target. We can see it there. So let's continue analysis, right? We can analyze, for example, second feature, which is the actual temperature. And you can see that we have pretty same thing there, right? So again, we tend to underestimate the demand for higher temperature. So now we can come up with the guess that maybe we trained our model on top of the period of time where we have just colder period of the year, and our model just learned the user's client's behavior during the winter. But later, the spring has happened, right? The temperature became better and better. The season conditions became better, and clients started to use bikes more often. But our model just didn't see such examples during the training period. And we know that this is the random forest, right? So it's not that good into extrapolation, right? And this is probably why we cannot go out of the ranges from the training period for our production period of time. So we can continue analyze this table. And the final question I want to answer there is whether we could catch something like this earlier. So maybe there were some chances to catch such thing, maybe during the first week of our production usage. Let's try to do it. For doing this, I suggest us quickly build the data drift report. So we still have some time, right? But for doing this, we are going to just use numerical features because we already saw that numerical features have more signal for the model in terms of the difference of the error comparing the majority objects with objects where we tend to underestimate or overestimate the demand. So let's regenerate the column mapping. Let's make it simpler. For data drift, we do not really need the targets and predictions because we're just analyzing the features, right? And let's create new dashboard. Now our tabs will be just data drift. So I just using only one tab in dashboard by chance. So definitely you can, for example, add here another tabs. I'm not doing it there because I already changed the column mapping, but definitely previously you could do it. So let's calculate our data drift and let's show it. So this is the pretty nice report where we have the interactive table with the distributions of our features. So we have the preview of the distribution for each feature on top of the reference and current data sets. And we have the information about whether data drift was detected or not, and the p-value for similarity tests. We have different statistical tests used for numerical and categorical features. For now, we have the Kolmogorov-Smirnov for numerical features and 2 tests for categorical features. Z-score for binary features and chi-square for features with more unique values. So let's analyze the drift. You can see that 4 features out of 6 are drifting. We have some statistics available there. And let's analyze the drifted feature. You can see that temperature feels like temperature, humidity, and wind speed is drifted. And obviously weekday and hour is not drifted, but this is something that we expected, right? So weekday and hour is something that does not change over the time, right? So let's analyze the temperature. Again, we can open up each row in the table and see the data drift visual, which is the visual where we have the average value for the feature, in this case, temperature calculated on top of the reference data, right? So we have the green, the light green zone which is related to one standard deviation from the mean value. And with gray points, we have the current values. So we can see that pretty often we have higher temperature comparing to something we see during the training. And we can analyze the distributions, which is the next step. And we can see that distributions are pretty different, right? So obviously we can do something like this and see how distribution for current period looks like, and vice versa. We can analyze the reference distributions, which we can see we have much, not that much maybe, but comparably lower temperatures, and we can put it back together to analyze it, right? So we can do same for other features, like feels like temperature, right? So again, we can see the trend to higher temperature. Here is our distributions, right? So we can see obviously that peak is much brighter for higher temperature, and we can analyze humidity, line speed, whatever, to see how it looks like. So many information there. So probably if we created the data drift dashboard from the very beginning, even after the first week of production usage, let's say simulated production usage, we could catch that something is happening with our input data. And if we had some information about feature importance, we could conclude that we should take some actions, because our pretty important features like temperature, wind speed, and humidity are drifting. So something is changing. This is why the data drift is often used as the early monitoring, because even before we got some information about our ground truth, especially if you have this ground truth with the delay, which sometimes is happening due to some software reasons, right, or some process reasons, then we almost always have our features without any delay, because the features is used to generate in the model's output, so we can just quickly generate it and save it while someone is using our model. So we can create the data drift dashboard and see what is happening. And yeah, it's almost always handy to create this kind of visual interactive dashboard, especially where we analyzing the model, right? But when we try to build some production pipeline, it's much easier and much useful, let's say, to generate some metrics as the digits, right? And integrate it with your monitoring tools like Grafana or maybe Zabbix or something like this. And in this case, you could use the Evidently profile, which is more or less the same thing as the Evidently dashboard, but profile is the JSON format for our report. So it includes the same statistics and information, but in a JSON format. So you can print it out just to see how it looks like. And you can see, right, so there is some information about the kind of report, information about the feature names, right? And for example, you can get the feels like temperature here and get all the information about p-values and things like this. So it's, oh, sorry. No, I was right. So it's here. So it's always better to use pretty print for JSONs for have the hierarchical structure if you're going to actually read this JSON. So this is more or less all I wanted to share with you. I hope maybe you will find something interesting in these reports and the profiles. And of course, we will be happy if you comment, maybe try to use Evidently for your models and give us some feedback. Happy to answer to any questions.
Thanks a lot, Emeli. Really useful presentation, at least for me. Yeah, if any of the attendees have any questions, we can take that right now. I think before the Q&A, yeah, I think there's a question already.
Oh, I can fill the question if that's okay.
Yeah, sure.
So one question, is it possible to use with Streamlit or otherwise live, I imagine? And the answer is yes, with some details.
Yeah, sure. So I personally like Streamlit a lot because it has a very nice API and so on. And yes, Streamlit has some, let's say, functions to visualize digits, to visualize pandas data frames, right, and some plots. So we can use Evidently as a kind of, let's say, backend. I mean, you can calculate with help of Evidently some metrics and visualize it with help of Streamlit. And Streamlit also allows you to publish your dashboards. I mean, they can host it. So I believe it can be a good combination of tools.
And in terms of live integrations, we also have an integration with Grafana, which is already released, but we are adding some more. So basically, there is a way to use Evidently to provide all the metrics and set up a Grafana dashboard and to have it regularly updated. So check it out. I will also post the link in the chat.
Yeah, just a question, follow-up question from me. So out of the box, does Evidently has any underlying, database or metric store, or you expect, based on the usage, like they can export the metrics like the profile you mentioned and persist it if required? Is that the proposed approach? Or have you seen someone like, you guys are offering some, plan to offer at some point some database for storing these metrics as well?
This is the great question. Unfortunately, currently we do not have any storage, so it works as a library to calculate some values. This is why we have an example with this Grafana integration, and there we have also Prometheus, which stores the data for us, right? Yeah. But later we are going to create Evidently service with the ability to store some metrics for some period. I know it's very important when you build the monitoring system because, well, you need to store the information somewhere. For now, we suggest to use some external databases. And of course, not only Prometheus. If you prefer, for example, ClickHouse or some other databases, it will be easy because it's JSON format, so we can integrate.
Cool. Yeah, thanks. Yeah, again, like same follow-up. So I think this one is essentially the one we showed is essentially for real-time model. What about the pre-computed models? If it's like an offline one, how do you collect the ground truth first? And then how do we manage the drift for these kind of models? Because we also have that use case here. A lot of models are pre-computed, like they store their prediction beforehand, and then on real time it's consumed via an API, for instance. Yeah. So yeah, my question is, how do we manage the ground truth with Evidently for this kind of cases? Yeah.
So for now, we suggest to store ground truth as in a separate database or somewhere, but make sure that you can later join the ground truth with the feature description of the objects, right? Because for Evidently, it's super important to have it in the same CSV file or in the same pandas data frame, because we cannot now like read it from different data sources. So for now, we expect the user to perform this join himself, right? And then give to Evidently the whole data frame.
Okay. Also, maybe to add in terms of tooling. So right now, Evidently is very well suited for batch monitoring jobs. Yeah. Right, when you just like calculate like some drift score, and then based on this, you can maybe update the model or like have some other action. And we have also example integrations with Airflow or like any other scheduler that you might use. For example, to generate a drift step in your doc, and then if drift detected, you might generate a report, and if not, just log the output. So you can basically build some sort of workflow in the background for your models.
Yeah, that would be super cool to integrate it part of the workflows, and even for training as well, it can be interesting for us some point. Yeah.
So basically the integrations that we have right now as an examples are the Airflow, the Emeli, and now Grafana, which we see like a fairly popular tools, basically for experimentation, for batch jobs, and for real-time monitoring.
Yeah, definitely makes sense. Yeah. I don't see any questions coming in. So I think that's it. I think thanks a lot, Emeli and Elena. I think it was super useful. I think we also had a few data science sessions just before this, so a few people were, attending that as well. So I will share this with the data scientists in Go, and hopefully, I think if there is any follow-up questions, I will ask them to, maybe open up an issue in GitHub or directly reach out to you guys.
Yeah. We also have a Discord channel, so if you want to ask questions or contribute or chat about the tool, you can also join.
Yeah, definitely. Yeah, I think we expect to liberate some of this in Go as well, for sure. Cool, very useful. Thanks a lot for your time. I really appreciate it. And for others in the call, tomorrow we're gonna see the use case of reinforcement learning, how we are using reinforcement learning in Go. So if you're interested, please join tomorrow's session as well. Have a nice evening. Thanks, everyone.
Thank you. Bye-bye.
Bye.